Ladies and gentlemen, my name is Agnieszka Jedrzejewska, Assistant Professor at the Silesian University of Technology in Poland. It is my pleasure to begin this course on cracking of reinforced concrete structures with a lecture on modeling of cracking. I find it necessary to start with an explanation of the term modeling. Modeling is commonly associated with simulations of structures with computer implementations of mathematical models. Its meaning, however, should be broadened. By modeling, we should understand any activity in which a model of the structure is created to study its behavior under specific conditions. Regarding reinforced concrete structures, modeling of cracking will of course mean computer simulations of cracking, its initiation and propagation, as well as prediction of crack width. Modeling of cracking, however, relates also to experimental tests in which isolated parts of the structure are mocked up to study the crack formation mechanism, cracking patterns, and crack width. The last but not the least important aspect of modeling of cracking regards creation of analytical models derived from reinforced concrete mechanics. Such models are used to formulate calculation procedures for crack control in design codes. Although my today's lecture will focus on conventional understanding of modeling by computer simulations, I would like to make some brief comments about other before mentioned aspects. However, to facilitate understanding the lecture, I will take liberty in making some introductory notes on the phenomenon of cracking. After that, I will briefly discuss how the real behavior of structural elements can be studied on a laboratory scale. I will make a concise overview of the analytical models used for crack control. Only then I will move to the main part of the lecture, in which I will introduce you to the approaches used in modeling of cracks, present damage and failure criteria developed for concrete, and discuss how to model the bond between concrete and reinforcing steel. This being said, let us start with shedding some light on the background of cracking in reinforced concrete. In general, concrete cracks because it is a brittle material when subject to tensile strains. Nevertheless, cracks which can be formed throughout the whole life of the structure may have different origin, behavior, and effects on the structures. The cracks may form as early as in the fresh concrete, around the time of setting, when concrete is still in plastic state. This early damage to concrete is usually manifested by a pattern of hairline cracks visible on the surface of the element. Significant cracking can occur during the period of hardening of concrete, which may have significant impact on the structure during its service life. These early age cracks are formed due to the restraint of imposed deformations caused by cement hydration and may reach significant heights, depths, and widths, often exceeding allowable limits. These cracks can grow further in hardened concrete when service loads are superposed on the structure. The most well-known cracking is this observed in mature concrete, which is caused by mechanical loading acting on the structure during its operation, but also other actions such as additional imposed deformations during service life. Whatever the source of cracking, cracks can be further classified into macro and micro cracks. Micro cracks are small, pore-sized discontinuities in concrete components. They can be formed within the mortar or less frequently in the aggregates. The lamination between the aggregate and mortar is also not uncommon. They usually have random character and are spread over a larger area or through the volume of the element. Macro cracks, in turn, are what we usually call cracks. These are large cracks of considerable height and depth. The most important characteristic which distinguishes micro and macro cracks is the involvement of reinforcement in case of the latter ones. Let me say a few more words about microcracking of concrete. As mentioned before, microcracks can form both at the surface and in the volume of the element. Damage to concrete always initiates with formation of numerous microcracks, some of which later concentrate and create large macrocracks when reinforcement becomes involved into transfer of stresses. It can be said that formation of microcracks within the element somewhat contributes to the growth of the pore structure. Therefore, microcracking may have adverse impact on mechanical properties of concrete, such as strength and stiffness, due to the damage of the matrix. It also influences physical properties of concrete, especially those related to its permeability. Microcracking is the subject of studies on micro and mesoscopic level, which focuses on concrete itself, its morphology, chemical composition, and pore structure, and does not account for the presence of reinforcement and the impact of the composite work between steel and concrete on cracking. It will therefore not be the subject of this lecture. We will focus on macro cracking of concrete. Let us look at what happens in a reinforced concrete element subject to increasing loading. A crack is initiated when tensile capacity of concrete is reached in a certain location in an element. It is worth to mention here that the first crack may not necessarily form in the location of the extreme tensile stress, as there is always a trade-off between local stress and local strength. Concrete is not a homogeneous material, and the so-called weakest link governs the crack formation process. It is one of the challenges in modeling of reinforced concrete to define the tensile capacity in a sense of crack resistance of concrete. As strains in the element increase, the crack starts to open. Mind that the width of the crack differs along its depth. Especially, it may be different at the level of reinforcement and on the surface. This is important when the width of the crack is measured in an element. The on-site measurements usually provide the width of the crack measured on the surface, while in laboratory tests the measurement devices are often mounted on reinforcement and hence give the crack width in this location. Such a crack is the primary crack. It is followed by internal cracks which are formed due to activation of the bond between steel and concrete. As strains develop further, subsequent cracks are formed. At first, each crack is in a single crack stage, and there is no impact of the cracks on one another. At some point, however, the cracks are formed so close to each other that developing strains can no longer reach tensile capacity and cause further cracks to form. This stage is called stabilized cracking stage. Nevertheless, additional strains may develop in such a cracked element during its service life. Such additional loading may lead to formation of further cracks or opening of the existing ones. The latter case is especially dangerous because it may lead to exceeding the allowable limit value of the crack width. It should be remembered that concrete cracks, and it is usually acceptable until the width of the crack is below the allowable limit. Different actions cause cracking of concrete elements, and by observing cracking patterns, an experienced structural engineer can determine the reason of cracking. This is because certain structural elements behave in a certain way depending on the loading scheme, their geometry, and support conditions. Understanding of this behavior is fundamental before any modeling activities are undertaken. So how to properly mock up a structure, or preferably its parts, and test them on a laboratory scale? As I have just said a minute before, initiation, propagation, and pattern of cracking is associated with the mode of its work. Let me recall here classical academic examples of flexural tests. The 3- and 4-point bending tests are designed to investigate the behavior of flexural elements such as beams and slabs. We know that the mode of work of such elements will be governed by either bending or by shear. This will depend on a number of parameters such as the depth to effective span ratio or related to the applied longitudinal and transverse reinforcement. The mode of work will be manifested by the mode of failure, which we can distinguish by formation of either a splitting crack in the span or a shear crack near the support. There is a wide range of tests which can be performed to characterize cracking in reinforced concrete structures and structural elements. As for the cracking due to the action of mechanical loading, typical tests of concrete under tension or bending are performed, in which the load can be either monotonic or cyclic, and with a different rate of the applied strain. This allows to model the behavior of reinforced concrete elements under various typical as well as accidental loads to which they can be subjected during service life. When concrete elements are subjected to the action of imposed deformation, Their cracking resistance can be controlled with the tests of restraint deformations, including ring tests and linear frames, for example temperature stress testing machine. If cracking can be caused by superposition of mechanical loads and imposed deformations, the isolated elements or even parts of the structure can be mocked up in the real scale. In this case, it is essential that the actual support conditions are properly represented in the isolated tests. The main aim of modeling of cracking is to provide robust design procedures for crack control. That is why before I move to the complex simulations of cracking, I would like to make a concise overview of the analytical approaches. In general, the analytical models for crack width calculation define the crack width as a product of crack spacing, or slipping length, and strain difference between the cracks, which is called crack-inducing strain. Various approaches provide different methods to calculate crack spacing. There are some similarities between them that can be presented. First of all, in majority of cases, the crack spacing is derived for an end-restrained element in tension, so for a tie. The crack spacing depends on reinforcement, specifically on the degree of the applied reinforcement and the diameter of bars. According to some approaches, the crack spacing depends also on concrete cover, although there is no agreement between the methods on this. The formula which is derived for crack spacing in end-restrained element is further adjusted to represent any element under tension, so not necessarily pure tension, but also pure flexure and eccentric tension. The analytical approaches also provide guidance on how to determine the value of the crack-inducing strain. Usually, two representative cases are distinguished. The first scenario is that of an element restrained at its ends. Since cracking in such element changes forces globally, the crack-inducing strain is dependent on the degree of the applied reinforcement. In the methods, this strain is usually a function of the degree of reinforcement and tensile strength. The other scenario is that of an element restrained at its base. In this case, cracking changes forces locally, and the crack-inducing strain depends on the restrained part of the strain and extensibility of concrete, which means the ability of concrete to expand between the cracks. Numerous methods for crack width calculation can be found in the literature of the subject. There are a lot of similarities between them. However, there are also discrepancies which must be accounted for the robust use of these methods. In general, the following aspects should be addressed in the model for crack width calculation. The effective tensile strength, so the strength for which cracking occurs. The effective tension area, so the area of concrete section which is effectively engaged in transferring tensile stresses due to the limited range of impact of reinforcement. Influence of concrete cover. Tension stiffening effect of steel due to the bond between steel and reinforcement, and appropriate bond law to represent this behavior. Whether the model is based on the mechanical approach or calibrated, which will limit their range of application to the cases based on which it was derived. Distinction must be made for which crack stage calculations are made, and preferably calculation procedures should be differentiated to account for different behavior of cracks in the crack formation stage and stabilized crack stage. Distinctions should be also made for cracking at early age and in long term during service life. The conditions for which cracking may occur during hardening of concrete are different than in case of mature concrete. Moreover, the superposition of early age and long-term effects on the final width of crack should be accounted for to assess precisely the expected crack width. Finally, the model should account for the superposition of the effects of imposed deformations and generic mechanical load on the total width of the crack. All these aspects are also important when using more advanced models, such as those which are used for computer simulations. That's why, having in mind everything that was said so far, let us proceed to the main part of this lecture about computer-aided simulation of cracking. There are two basic approaches to modeling cracks. They are both usually based on the finite element method. The first approach is a discrete model of cracks, in which, as the name suggests, cracks are represented in a discrete manner. This approach is suitable to model the behavior of the elements with a few dominant cracks with known location and direction of propagation, for example, the laboratory experiments. The second approach is a smeared model of cracks, in which cracks are not represented as geometrical entities. Thanks to the easiness and flexibility of use of this model, it is suitable for analysis of generic structures with many cracks of small widths. Let us have a closer look at each approach. In a discrete model of cracking, each crack is modeled directly as a discontinuity of the finite element mesh. When the force in the node at the tip of the crack exceeds tensile capacity, the node is split in two and the tip of the crack propagates to the next node. The advantage of this method is the possibility to determine exact location of the crack and follow its growth. On the other hand, remeshing must be performed after each step in which new discontinuity is introduced. This is computationally challenging and hence is rather not used for modeling of whole structures and large structural components. For that purpose, the smeared cracking model is employed. In this approach, crack is not a discrete phenomenon and no discontinuity is introduced to the mesh. Concrete in this approach is treated as continuum, before cracking as a homogeneous solid with isotropic properties. After cracking, the crack parts, or more precisely, cracked finite elements, are assigned with modified properties and the material of the cracked part is no longer isotropic. Usually, the cracked element can no longer transfer tensile stresses, but can still transfer shear stresses. Characteristics of each finite element before and after cracking are defined by the applied damage criterion. The simplest way to determine whether cracking occurred is to compare the tensile strain or stress in the structure with tensile capacity of concrete. The main challenge is to define this tensile capacity. If concrete in the whole analyzed element is assigned with uniform mechanical properties, the question usually is which tensile capacity should be chosen to represent cracking resistance of concrete. One of the choices is to operate with mean tensile strength, while others advocate to use 5% quantile value to account for the effect of the weakest link. If formation of the crack is expected to happen in a certain location, localized strength reduction is introduced, which is an analogical concept to the introduction of the notch in the beam. Once the cracking is initiated, the behavior of the cracked material must be defined to follow the progress of cracking. This behavior is described by damage models. Damage models base on the assumption that compressive stresses are relatively low with respect to the compressive strength of concrete and that concrete degrades in tension. It is assumed that a part of the finite element is sound and a part is cracked. The sound part of the element can transfer further stresses. The level of stress which can be still transferred by the element in which cracking was identified is defined by the parameter called damage. For an uncracked element, the damage is zero and the element can take full stress. With progressing damage to the element associated with progressing cracking, the value of the damage parameter increases and the efficiency to transfer stresses by the element decreases. This means that the damage parameter describes the softening behavior in tension. The constitutive behavior of concrete in tension in the damage models is described by two relationships. Stress-strain relationship before cracking, which for concrete is usually defined by a bilinear relationship, and the softening behavior after formation of the crack associated with the crack opening. In smeared cracking models, in which the crack is not physically represented, the crack opening is simulated with the so-called crack strain. The width of the crack can be then calculated from the value of this cracking strain. To make this solution independent of the size of the mesh, which would otherwise impose the location of the crack and its development, the characteristic length, also called a crack bandwidth, is used, which depends on the fracture energy of concrete. Damage models are usually based on one-dimensional analysis of stresses. That is because in the elements analyzed with these approaches, there is one dominant principal stress which is tensile and which can cause cracking. However, some structural concrete elements undergo failure in complex stress states. Such complete definition of the material's behavior under any stress state is done with the material model and failure criterion. For a three-dimensional stress state, failure criterion can be represented with a failure surface in the space of principal stresses. Points on the surface represent stress states for which failure occurs. Failure criteria for concrete have been developed since the end of the 19th century and have been improved to better represent the behavior of concrete. The number of proposed failure criteria and peculiarities of each proposal makes the subject so broad that it could be the topic of a separate lecture. What is important is that the failure surfaces are created based on laboratory tests of concrete for characteristic stress states, such as uniaxial, biaxial, and triaxial tensile and compressive strength. Strengths of concrete under these specific stress states serve as a basis for creation of the surface. It is also known that the meridians of the failure surface are not straight lines because the deviatoric section becomes closer to circular in the zone of tensile stresses. The criteria are represented by introduction of the cap in that area or by describing the meridians as smooth, curved lines. Moreover, the axiatoric section of the surface is not circular and it is not a solid of revolution. If the applied material model accounts for plasticity, such as in case of concrete in compression, two surfaces are defined: the failure surface and additionally the yield surface, and they are usually based on the same criterion. It is interesting to add that failure criterion can be used not only for mature concrete, but also for concrete in the hardening phase. Since the surface is defined based on the strengths of concrete, and given that these strengths develop with progressing cement hydration, this is represented by growing of the failure surface. From the point of view of modeling, the calculations of hardening concrete are performed with an incremental approach for discrete time steps. In each step, the failure surface is redefined according to the assumptions of the failure criterion for the current values of the strengths. The applied material model in turn defines the path of the stress within the surface, as well as the behavior of the surface when it is reached. Let me explain it on an example of the standard material model of concrete under uniaxial compression. This elastoplastic model requires definition of both yield surface and failure surface. As long as stress is below the elasticity limit of concrete, the material behaves in an elastic manner and the point representing the stress is inside the yield surface. When elasticity limit is reached, it means that the point is on the yield surface. Now the applied flow rule defines the behavior of the material under increasing strains. In case of isotropic hardening, this is manifested with uniform growing of the yield surface until it reaches the failure surface and coincides with it. This means that the material has reached its compressive strength in this point. The ascending branch of the stress strain diagram represents the behavior of the failure surface after fracture, which in this case would be progressing degradation of concrete until total failure. Depending on the location where failure surface is reached, fracture is manifested with different modes of crack. If failure surface is reached within the zone of tensile stresses, a splitting crack is formed. Such a case can be simplified to a one-dimensional damage analysis. In case if concrete fails under compression or any complex stress state, the crack mode can be different. In general, there are three modes of cracks. Opening mode, in which a splitting crack is formed. This is a commonly known crack which is formed under tension. When concrete fails under compression, such as for example in uniaxial compression test, a sliding mode of fracture occurs with a shear crack. Finally, a mixed mode of the two can occur, which leads to a tearing crack. In the slide you can see a map of stresses in a half of a reinforced concrete wall, in which a contraction caused by shrinkage is restrained by a foundation. In such a case, the horizontal stress is equivalent with one of the principal stresses and causes tension in the wall and compression in the foundation. The following map of damage intensity shows the level of stress with respect to tensile capacity of concrete. Black color means that the damage intensity factor is equal to 1, which in this case is equivalent with reaching tensile strength. Based on the philosophy of smear crack image, we can deduce that splitting cracks are formed in the black areas. It is possible to follow their direction of propagation and opening. The crack is formed in the direction perpendicular to the principal tensile stress. That is why we can expect vertical cracks in the central part of the wall, which tend to lean down towards free ends of the wall, and a disjoining crack is formed at the end of the wall foundation joint. A lot has been said about modeling of concrete, while modeling of reinforcement is of the same importance. Let me briefly present you what approaches are available to modeling of reinforcement. First of all, the distributed or smeared model, in which reinforcement is modeled with the use of a substitute material which is composed of concrete and reinforcement and has strong anisotropic properties, and in such a way the reinforcement is located in the direction of real reinforcement. Alternatively, an embedded model can be used, in which reinforcement, which is modeled with a bar, is superimposed on the concrete elements in the finite element mesh, and bars pass through concrete elements in an arbitrary manner. Finally, the most commonly used model for reinforcement is a discrete model. In this model, reinforcement is represented with its real location and real material properties. It is modeled with linear one-dimensional elements, so bars, which are connected with the nodes of a two-dimensional or three-dimensional concrete element. The deformation compatibility is ensured in the nodes between steel and reinforcement, and appropriate bond law must be defined to tell what is happening at the interface between reinforcement and concrete. The last property, which is crucial for proper modeling of reinforced concrete, is a bond between reinforcing bars and surrounding concrete. I have said at the beginning of this lecture that a fundamental characteristic of a macro crack is the bridging effect of reinforcing steel on the formation and development of cracks. Thanks to that bond, in cracked cross-sections, the tension forces in the crack are transferred deeper into the uncracked parts of the concrete element by reinforcing steel. Let us imagine the case of a tie in a crack formation stage. The absolute displacements of steel and of concrete along the transmission length are different. This relative displacement generates bond stresses between concrete and steel. Along the transmission length, a part of the tension force of the reinforcing steel, which is acting in the crack, is transferred into the concrete by bond. This effect is called tension stiffening. This bond behavior depends on a number of factors, which include the type of loading, the factors which are related to concrete, such as concrete properties, concrete cover and casting position, and of course factors which are related to reinforcing steel, such as its class, the applied diameter of bars and their spacing, the conditions of the bar, and transverse reinforcement. In practical engineering applications, it is convenient to assume that the mean bond stress is independent of the crack width. In such applications, for example in design codes, the mean bond stress is represented in relation to the mean tensile strength of concrete. However, it must be remembered that bond stresses change with the slip, so while the crack develops, and it is important to account for this fact in the model to obtain realistic results. The bond-slip law depends also on the mode of failure of the element under tension. When reinforcing bars have enough confinement provided by thick concrete cover or secondary reinforcement, the bar is pulled out of concrete volume. In an opposite situation, so when the confinement is insufficient, the element fails by splitting of the concrete cover. Consequently, the bond-slip law has the following form. The first curved part refers to the stage in which the ribs penetrate into the mortar matrix. It is characterized by local crushing and microcracking. In case of unconfined concrete, splitting failure occurs, which is reflected by a sudden drop of the bond strength. The horizontal level occurs only for confined concrete. It reflects advanced crushing and shearing off of the concrete between the ribs of the bar. This level represents a residual bond capacity, which is maintained by large concrete cover or transverse reinforcement, keeping a certain degree of integrity intact. The decreasing branch refers to the reduction of bond resistance due to sharing of the concrete corbels between the ribs. I would like to close up this lecture by presentation of two examples of application of crack models. The first one is related to the use of a discrete crack model to follow the propagation of a crack in an atypical notched beam and verify the model against the experiment. We can see here how a discrete crack is being formed by introduction of discontinuity of the mesh, which requires remeshing in the close vicinity of the crack path. This is a good example of application of a discrete model in an element with one dominant crack of predefined location. It is known that the crack will initiate at the tip of the notch, and the analysis will progress from this node. The second example shows the use of a smeared model to analyze the width of cracks in a beam under 4-point bending. The width of the crack is derived from the cracking strain with the use of the crack band concept. The locations of the cracks are identified with a damage criterion. Cracks are formed when tensile capacity is reached, and in the finite elements in which cracking occurred, the softening behavior is described by the cracking strain. The results of the model are compared with the experimental tests to check the obtained crack spacing and crack width. Given the large amount of cracks whose location is not known prior to modeling, the use of the discrete model would be highly inefficient, while the smeared model allowed to obtain the desired results with less computational effort and still satisfactory compliance. Thank you very much for your attention during this lecture. If this lecture was interesting for you and you have any further questions which you cannot ask today, please don't hesitate to contact me. I am providing you here my contact details, including my phone number, my email address, or you can also visit my personal web pages. I would also like to invite everyone to join our RILEM Technical Committee on Early Age and Long-Term Cracking and contribute to the works of this interesting committee. Using this opportunity, I would also like to invite you to participate in the conference Synercrete, which will be organized on the Milos Island in Greece in June 2023. I have a pleasure of co-organizing this conference together with, among the others, Miguel Azenia and Fakulis Kanavaris, whom you have already met. The topic of this conference is synergizing expertise towards sustainability and robustness of cement-based materials and concrete structures. I encourage you to visit the webpage of the conference where you can find further details about the conference, conference topics, participation conditions, and submission of your papers. Also, if you have some specific questions, you can also contact me directly. Thank you once again.